2453, 2453, destroy sequential targets. This is a pretty new problem on Leetcode, fresh off the lot, ready to be solved, and I hope you learned something from me approaching this problem today. We're going to destroy this problem sequentially like it's an enemy target. Okay, so you are given a zero indexed array nums consisting of positive integers representing targets on a number line. You are also given an integer space. You have a machine which can destroy targets. Seeding the machine with some nums I allow it to destroy all targets with values that can be represented as nums I plus c times space, where c is any non-negative integer, where you want to destroy the maximum number of targets in C. Okay, so we can destroy any number y such that y equals space times c plus nums I. So this already looks like the definition of division here, or with the remainder, right? You want to return the minimum values of nums I you can seed the machine with to destroy the maximum number of targets. Okay, so this language here is always found this a little bit confusing. What this is basically saying is you want to destroy the maximum number of targets, but if you're in a situation where there's multiple nums I solutions that would destroy the maximum number of targets, then return the minimum one, right? It's not saying something else like you want a combination of a minimum value plus the maximum value, you want to minimize that. No, you just want to maximize the ones you can destroy. If there's multiple such solutions, choose the smallest such solution. Such it is. Okay, so let's just go ahead and look at this example. Well, we have nums equals, can I get this lined up right? Close enough. We have nums equals 3, 7, 8, 1, 1, 5, and we have space equals 2. So really what this question comes down to is find a number, and if each in such that there's a space offset between additional numbers, and you can destroy that number. So if you have like space equals 2, you can destroy each y such that 2 times c plus nums of I equals y for each c in positive integers, so, or non-zero integers, right? So if we were to choose 3, we could destroy 3 because 3 equals 2 times 0 plus 3. You could destroy 5, 2 times 1 plus 3. Destroy 7 because that's 2 times 2 plus 3. Destroy 9, 2 times 2 plus 2 times 3 plus 3, right? And these, of course, each of these are going to be, you know, plus 2 increments because we have affine function. So 3 can destroy 3, 5, and 7. And likewise, if we choose just 7, right? If we choose just 7, we can destroy just 7, right? Because C has to be non-negative. 8, we can choose just 8. If we choose 1, we can destroy 1. Sure, 3, 5, and we can destroy 7. So obviously, in this case, 1 is the optimal solution because there's a maximum number of nums, which are 2 increments, you know, size 2 increments away from 1. So this would return 1. Okay. So when you look at this problem, the way you want to think about solving it is to consider, what? I'm just trying to talk. Well, if you're familiar with modular arithmetic, or if you've taken a discrete math class, or, you know, an advanced algebra class, or, you know, college, whatever, mathematics course, you're familiar with this idea of modular arithmetic in remainders. And this should look very familiar, right? Because this is the definition of like a remainder function. But I'm not going to bore you too much with the kind of convoluted nature of mathematics. So we're just going to focus on kind of the intuition behind how that can apply to this problem. So C can be anything. So when we multiply C times space, we're going to get as close as possible to the number we're trying to destroy. And we can only destroy that number if the remainder nums I doesn't get in the way, right? So when we destroy 3, we can destroy anything that is 3 plus C times 2 away, right? So that means we can destroy anything that is remainder 1 from Y away. Because we can multiply C times space to get Y, right? Minus some remainder J for all numbers, right? For any number, it can be the case that this solution holds, right? For C times 2, then, right? There's always a way to get a number that is J away from our destination number Y, right? So for 7, for example, for 3, for 7, let's look at 7, right? C times 2 equals 7 minus J, right? We can say, okay, well, C equals 3 and J equals 1, right? And that's true for any number. So what we're going to do is we're going to create a mod space based on this J value. So we'll look at each number and mod it by space and find where it belongs in this destination array. Okay? So the mod space can only be as long as space is itself. So let's do a different example here. Oh, they're all space too. But if we did let's just do an example where space equals 3. So if space equals 3 and we look at this problem, right, that means that there's 3 spots in space because there's only 3 total places where mod 3 you could end up. So 3 mod 3 is 0, so this becomes 1. 3 mod 7, wrong direction. 7 mod 3 is 1, so 1 becomes 1. 8 mod 3 is 2, so this becomes 1. 1 mod 3 is 1, so this becomes 2. 1 mod 3 equals 1, so this becomes 3. And 5 mod 3 equals 2, so this becomes 2. So our final is 1, 3, 2. Right? Because for all of these numbers, with respect to space, we can always find a C times this value such that it equals, or C times 3 such that it equals this value minus what remains in here, right? So this would be this blue line representing 0, 1, and 2. Right, so there's 3 cases where there's 1 remaining here, right? Well, if this is C times space equals Y minus J, well, that's the same thing as Y equals C times space plus J. And, well, if you look at this equation and compare it to this initial equation, that's just nums of I. Right, so J is really nums of I as your starting value. So therefore we just need to find the nums of I that maximizes this array that we created here. Okay, so the first thing we'll do is we'll create this mod space. So mod space equals default dict lambda 0. We're choosing to make this a default dict because space can be really big, right? Space can be 10 to the 9, and we don't want to create 10 to the 9 space because it's very likely, right, we only have 10 to the 5 actual numbers that we have to look at. So let's not constrain our space to 10 to the 9 because it's going to be very slow. Okay? Then we'll look at each num and nums, and we'll find that j, right? That j value we were talking about. So we'll say mod space of num mod space plus equals 1. Okay? And then we'll just assume that the minimum number is num 0. And then we'll look at each num and nums. We'll say, well, if mod space of this num mod space, right? So if the j value that this number belongs to is greater than the j value of the current minimum that we're trying to find, or they're equal and the current number is less than min num, in that case min num will then be the current number, and at the end we just return whatever that min num is. Keep writing mode space. Ooh, what did I do wrong here? So we take mod space, we mod the number by space, we assume the first number is the smallest. We say if this num, or equal to, sorry, forgot to change that. Alright, and then we do that, and that's it. So I think this is one of those problems where it's kind of unfair to assume that somebody without a background in discrete mathematics or modular arithmetic or, you know, advanced calculus or whatever would be able to comprehend this. But there is some intuition behind it. I suppose that you could figure it out if you thought of it kind of intuitively. But personally, I looked at this problem and noticed that I was looking at the formula for a remainder, and then it kind of just developed from there. Okay, thank you. Have a good day.